Hello and welcome to this FMSP online revision recording for the OCR specification, Module M2, Mechanics. The topic is motion of a projectile. And in the specification under that heading, we see these three sections. Model the motion of a projectile as a particle, moving with constant acceleration. In other words, we're going to consider that the only acceleration acting is downwards due to gravity, and we're going to treat the projectile as a particle. So, for example, we're going to be able to ignore air resistance, and in fact anything else that goes on in the air, wind speed or turbulence. And by modelling the projectile as a particle, we're going to ignore its length, or any rotation as it moves through the air. And these are limitations of the model. The second point is that we're going to use horizontal and vertical equations of motion to solve problems. In other words, we're going to use the Suvat equations in two perpendicular directions. Although it then says, including finding the magnitude and direction of the velocity, which of course is a vector with magnitude and direction. So we may find we have to recombine our perpendicular components in order to find information about the velocity as a vector. Then we might also be asked to find the range on a horizontal plane, which is how far along the plane before the projectile strikes ground level again, and the greatest height reached. The third point says we should be able to derive and use the Cartesian equation, that is the x and y equation, of the trajectory. It's not enough just to memorize the trajectory equation. We may have to derive it on demand before using it to solve a problem, and that's just what we do need for the second exam question that I've chosen to use in this presentation. Now let's look at some key points. First of all, we are considering the horizontal motion separately to the vertical motion. Why? Because horizontally there's no acceleration, but vertically there is an acceleration. So we get different equations whether we look horizontally or vertically. Let's consider the projection of the particle. If it's projected at a certain speed, let's say u, at an angle of theta degrees to the horizontal, well, we can find out from that the components for the vertical and the horizontal initial speed. U cos theta for the horizontal initial speed, u sin theta for the initial vertical speed. But because there's no acceleration horizontally, any later speed horizontally is still u cos theta. That doesn't change. Whereas you'd need to use v equals u plus at to find an equivalent expression for the vertical velocity because of the acceleration of minus g. And again, there's a nice simple expression for the horizontal displacement. It's simply distance equals speed times time because there's no acceleration. But you'd have to use s equals ut plus a half at squared to derive a similar expression for the vertical displacement. So here's the equation of the trajectory, and how would you derive it from scratch? Well, you'd make t the subject of this expression which we've just seen above, so rearrange that to say t equals, and use it to replace t in the expression for the vertical displacement, and then you'll be left with an equation linking just y and x. And you'll see me do that in one of the questions. So here's our first exam question. A particle is projected horizontally with a speed of 7 meters per second from a point 10 meters above horizontal ground. So here we go, from a point up here, it's projected at 7 meters per second. It's going to follow a parabolic path and strike the ground somewhere over here at a point I'll label A for reference, and we're told the particle moves freely under gravity. So the only acceleration is that due to gravity downwards. We're asked to find the speed and direction of the motion, in other words of the velocity of the particle at the instant when it hits the ground. One further point to make, which is, like I always do, I'm going to take upwards as being the positive direction. You might quite reasonably take downwards as being positive in this case, because all the vertical motion is downwards, but I'm going to stick with upwards because I consistently do that. So let's write down what we know. Firstly, horizontally. The particle was initially projected at a speed of 7 meters per second horizontally, but the acceleration is 0, which means later on v equals u plus at, if you like, and a is 0, so v is simply equal to the initial speed. So that hasn't changed. There's the horizontal component of the velocity. Now for the vertical component. Well, initially, vertically, the component of the speed was 0, but it has an acceleration of minus 9.8 meters per second squared. Physicists, don't forget, don't use 9.81. We're instructed to use 9.8 on the cover of the OCR exam paper for mechanics. And what else do we know about it when it hits ground? It's gone down 10 meters. And we're trying to find the vertical component of the velocity now. Well, given u, a, s and v, v squared equals u squared plus 2as is the most efficient way of getting the answer. V I'm trying to find, but u squared is 0 squared, that's 0, plus 2 times an acceleration of minus 9.8 times a displacement of minus 10. So v squared equals 0 plus, well this is going to come out positive because of the two negatives multiplied together, and I have 10 times 9.8 is 98, times 2 is 196. Well, that's handy because that's a square number. So v is positive or negative 14. But think about it. I've chosen upwards as positive, and the only vertical motion for this particle is downwards. So it must be the minus 14 that I need in this case. Okay, so let's draw what we know. The particle is striking the ground. It's coming in with a velocity in this sort of direction, where there's a horizontal component of 7 meters per second and a vertical component of 14 meters per second. And we want to find the speed. Well, as it's a right-angled triangle, we can use Pythagoras. It's simply the square root of 7 squared plus 14 squared. And I calculate that to be 15.7 meters per second to 3 significant figures. Having found the speed, we need to find something about direction. The question said calculate the speed and direction of motion. It didn't tell us how to give the direction. I think I would give the angle from the horizontal. So if I'm giving that angle alpha, that by alternate angles is the same as this angle up here, and tan of alpha equals the opposite, which is 14, over the adjacent, which is 7. Well, that's nice. That just means tan of alpha is 2. So alpha is tan to the minus 1 of 2, and I calculate that to be 63.4 degrees to 1 decimal place. And even from my fairly sketchy diagram above, I could believe that was the right angle. And I'm just going to say then that it's 63.4 degrees to the horizontal ground. It isn't a problem if you calculate the angle from the vertical, as long as you state clearly that that's what you're doing. And how is this question marked? Well, for 6 marks, there's no mark at all for saying that the horizontal component of the velocity is 7 meters per second. The first mark awarded is a method mark for using the correct Suvat equation, and finding, for the second mark, the vertical component of the velocity to be 14 meters per second downwards. The next 2 marks are one for using Pythagoras and one for calculating the correct speed, followed by one for using trigonometry and one for getting the correct angle. And one last point about that, which is I chose to use tan because I had these 2 nice integer values rather than use the calculated value of 15.7, which again, because it's dependent on previous answers, may have been incorrect. So I used my best numbers to go into tan rather than use sine or cos. Well, let's move on to another question. This time, a particle is projected with a speed 7 meters per second from a point O. And I'm particularly told that the horizontal and vertical displacements are going to be x and y meters. So I need really to think as though I'm drawing this on an xy graph. And here's my particle motion, my projectile motion. And the initial speed is once again 7 meters per second at an angle, in this case, of 30 degrees as the angle of elevation, so above the horizontal. We're told the particle moves freely under gravity. So again, it's just gravity acting as the acceleration downwards. Well, I'm going to need to split that initial speed of 7 into components horizontal and vertical. And the horizontal component, the one next to the angle, will be 7 cos 30, and the vertical component 7 sine 30 degrees. What do we need to do with that? Express x and y in terms of t. So we're looking for 2 expressions, x in terms of t and y in terms of t. And then, hence, putting those together, find the equation of the trajectory of the particle. So they've reminded us how to do that. Okay, let's go ahead with that then. First of all, what have we got horizontally? Well, the horizontal speed initially was 7 cos 30 degrees. The acceleration is 0, and so if we use for displacement s equals ut plus a half at squared, my horizontal displacement, which is the x displacement, is the initial speed 7 cos 30 degrees times t plus a half at squared, but of course a is 0, so that's all we get. And I'm just going to, while I'm still on that side, rearrange and say that that means t will be x over 7 cos 30 degrees. Because this is what I'm going to come back to later for the substitution part. Now let's see what's happening vertically. The initial speed vertically is 7 sine 30 degrees. And the acceleration is, well, this time I'm going to leave it as minus g. And again, using s equals ut plus a half at squared, what do I get? Well, the vertical displacement is y. The initial vertical speed was 7 sine 30 degrees, and that is multiplied by t, plus a half of a. Well, that's plus a half of minus g, so it's minus a half of g times t squared. And there's my expression for y in terms of t. And now we substitute for t. So I'm simply going to use this expression and replace t on the right. Y equals 7 sine 30 t. So 7 sine 30 times x over 7 cos 30 minus g over 2 times t squared. So it's x over 7 cos 30 again, but this time squared. Well, let's tidy that up a bit. I notice in this first term that I have a 7 in the numerator and the denominator, so they'll cancel, and I have sine theta divided by cos theta, which is tan of theta, tan of 30 in this case. And we normally place the x first and say x tan 30 rather than tan 30x. Minus, well, there's nothing much else I can do apart from write all this out. On the top I have g and then x, which is squared, so gx squared. And on the bottom, 2 times 7 squared cos squared 30. 7 squared is 49 and 2 of those is 98. And then cos squared of 30 degrees. And there we go, there's the equation of the trajectory. That was for 4 marks, and the marks were as follows. 1 for the expression for x in terms of t, and 1 for y in terms of t. There's a method mark for attempting to substitute for t in the y expression, and then an answer mark for getting the right equation for the trajectory. Now let's see what we've got to do with that. Well, first of all, calculate the values, notice that's plural, of x when y is 0.6. So you're finding x values when y is a certain height. Well, of course, because the graph is symmetrical, you're expecting to get 2 values, assuming that that isn't actually when you're at the very top of the trajectory. And then find the direction of motion of the particle when y is 0.6 and the particle is rising. So it'll be this one rather than this value that you use for part 3. Okay, so let's proceed with that. What I'm going to do is just write down the equation of the trajectory again. I've got y equals x tan 30 minus g over x squared, gx squared over 98 cos squared 30. And we're told what happens when y equals 0.6. Well, we're going to get 0.6 equals x. Now, tan 30 has an exact value. It's not to say that you couldn't do the rest of this calculation using decimals, but I'm going to use the exact values so that I get the best possible looking calculation and don't lose any accuracy. G is 9.8x squared. I've chosen to substitute that in because on the bottom there's 98. Now, cos of 30 is root 3 over 2. So by the time I've squared it, I get root 3 squared over 2 squared. So that's 98 times 3/4. Well, let's see what else I can do with this. I have 0.6 equals x over root 3 minus, well, I've got 9.8 and 98, so I can cancel those to get a 10 on the bottom. I've got x squared over 10 times 3/4. Well, looking at that, I thought what I would do next is deal with that times 3/4 on the bottom, because that's the same if you're dividing by 3/4 as multiplying by 4/3. So I'm going to get x squared over 10 times 4 over 3, 4x squared over 30. Well, it's not looking so bad, but I'm not very keen on having that decimal on the left, nor particularly the root 3, but there we go. So the next thing I'm going to do is multiply through by root 3 to get, for this second term, root 3 over root 3, I'm going to get root 3x over 3. Of course, if you were just dealing with decimals, you might have got to an answer before now. But I want to have a nice looking equation. Well, I'm now going to multiply through by 30. That'll get rid of the 30 at the end there, and I'll just have minus 4x. By the way, I've lost the squared, which I'm just popping back in. That should be minus 4x squared. This term multiplied by 30 will give me 10 lots of what's on the top, 10 root 3x, and 30 times 0.6 is 18. I'm going to move that all to the left then, so I get 4x squared minus 10 root 3x plus 18 equals 0. My last step is going to be to halve all that and get 2x squared minus 5 root 3x plus 9 equals 0. Well, it doesn't look marvellous, but at least it has fairly nice coefficients to deal with. I've got to solve that. Okay, I'm going to write it up here to remind myself what I'm solving. So a is 2, b is minus 5 root 3, and c is 9. Clearly with that root 3 in the middle it's not going to factorise, so I'm going to use the equation. X equals minus b, so that's positive 5 root 3, plus or minus the square root of b squared, so that's 5 squared times root 3 squared, so that's 25 times 3, 75, minus 4 times a, which is 2, times c, which is 9, all over 2a, which is 2 2's, which is 4. So I've got x equals 5 root 3 plus or minus, well, 75 minus 4 times 2 is 8, 8 9s are 72, 75 takes 72 is 3. That actually is another root 3. And now you can see why I stuck to using exact form, because I've now got two answers, one of which is 5 root 3 plus another root 3, that's 6 root 3 over 4. In other words, 3 root 3 over 2, or if I subtract 5 root 3, take another root 3, which is 4 root 3 over 4, so my other answer is the square root of 3. As decimals then, if you want to see them, 3 root 3 over 2 is 2.60 meters. It's a displacement, remember, and the other answer is 1.73 meters, and both of those to 3 significant figures. Well, I've got two answers because that's the displacement on the way up when the height is 0.6, and this is the displacement when it's on the way back down and the height is 0.6. And if you're interested where 4 marks were allocated in the marking of this, 1 mark is for making the left-hand side equal to 0.6 and forming the quadratic equation. So there's a method mark for doing that. Using the formula to solve as a method mark, and then arriving at the two answers either in surd form or decimal form are the remaining 2 marks. So we know that we want this particular value for x, or in fact exactly root 3, to carry through to the next part of the question. Okay, so let's now find how it's travelling at that particular time. This is part 3, and again a little bit of suvat to work out what it is that we know. What we want is when the particle is rising and the horizontal displacement is root 3, and we know y is 0.6. So we know x and y, but what we could do with knowing is the component of the velocity, because we want to know the speed and the angle to answer the question. So horizontally, what do we know? Well, all the way across, v is 7 cos 30 degrees. That was the initial speed, and it's the final speed, it's the unchanging speed. Cos 30 is also something I could write in surd form. cos 30 is root 3 over 2. So there's an exact expression for that component of the velocity. Now for the vertical component, what do we know? We know the initial speed, which is 7 sine 30 degrees. And of course sine 30 is a half, so this is 7 over 2. I know s is 0.6. I know the acceleration is minus 9.8. And what we're trying to find is what's the vertical component of the velocity. So it's v I'm trying to find. Well, given what's there, I think once again v squared equals u squared plus 2as is what I need to use. And v squared equals u squared. Well, that's 7 over 2 squared, which of course is 49 over 4, minus 2 times a, and a is minus 9.8. By the way, I said minus and I should have written the plus here and reserved the minus for in front of the 9.8. Multiply that by s, which is my y above, my displacement, 0.6. Well, I won't bore you with the calculation, but whether you do it as decimals or fractions, you end up with a very nice answer there, that v is 0.7 meters per second exactly. So what's happening? The particle is rising, so its motion is in this sort of direction. And what do we know about the two components? We found out that the horizontal component is 7 root 3 over 2, and that the vertical component is 0.7. So the question, I'm just going to check and see the exact wording of the question to make sure that I answer it in the form they want. Find the direction of motion of the particle. Well, I think I'd probably give the direction of the motion as from the horizontal, because that's the kind of angle we were given to start with. So what can I say about theta? That tan of theta equals the opposite, 0.7, divided by the adjacent, which is 7 root 3 over 2. And I happen to notice, whilst calculating that in fact that's quite a nice exact value as well. It's root 3 over 15, which you could arrive at if you used 0.7 as 7/10 and turned it into a single fraction. Doing inverse tan then, I found an angle of 6.59 degrees to the horizontal. And I've given that there to 1 decimal place. I'm sorry, to 3 significant figures. I normally give angles to 1 decimal place, but because it was such a small angle, I felt I wasn't giving enough accuracy. Okay, one comment, which is I've given the angle to the horizontal, but you could just as well have given the angle to the vertical, and that would be fine, 83.4 degrees to the vertical. And how were the marks awarded? Well, firstly, there's 1 for finding an expression for v over here. There weren't any marks for the value of v horizontally. Arriving at 0.7 was the second mark. Using tan to solve and coming up with a correct answer were the final method and answer marks for that question. Well, I hope that was a useful reminder about projectiles. Don't forget to look at the other revision videos on the FMSP website.